Welcome back to Revise and Resubmit for another deep dive.
Yeah.
You know, their Weekend Classics episode with Pavlov and Nikita really got me thinking about Irina Grekova,
Oh, yeah.
a mathematician and ADD, a novelist. Not your everyday combo.
It really is quite remarkable. And actually, her pen name, Irina Grekova, it kind of hints at her mathematical background.
Oh, really?
In Russian, the Greek letter, the one used in math is pronounced Y. So it's like a subtle nod to her expertise hidden in plain sight.
Like a secret code, almost.
Yeah.
And getting a Ph.D. in math during the Soviet era,
Right.
that couldn't have been easy, especially for a woman at that time.
Absolutely. It really speaks to her determination and talent. Not to mention, she also wrote influential textbooks on probability theory.
Wow.
And Ezzy award-winning novels. Talk about a multifaceted mind.
It's really incredible. So where did this incredible journey begin? What shaped her path?
Well, it seems mathematics was practically woven into her life from a very early age.
Okay.
Her father was a math teacher, and he believed that advanced mathematics was actually simpler than basic arithmetic.
Hold on. Simpler. That's a bold statement.
It is, but he really believed it. And get this, he started teaching Grekova advanced mathematical concepts when she was just a child.
Wow. So she was tackling calculus before most kids are even mastering multiplication.
Exactly.
Right.
Imagine that.
It's incredible. I wonder if that early immersion played a role in her later success.
It's certainly an intriguing thought. From there, she went on to study at Petrograd University, now known as St. Petersburg State University, during the 1920s.
Wow, the 1920s. That must have been an exciting time to be immersed in the world of mathematics. Was the university a hub for mathematical innovation back then?
Absolutely. It was a vibrant intellectual scene.
I bet.
Think about it. Grekova was surrounded by some of the greatest mathematical minds of the time, like Boris Delaunay and Ivan Vinogradov.
Oh, wow.
These were pioneers pushing the boundaries of mathematical thought.
I can only imagine the conversations happening in the hallways, the lectures filling those classrooms. What an environment to learn and grow in.
You can almost feel the intellectual energy, right?
Definitely. So after graduating, what did she do?
Well, she embarked on a long and distinguished academic career. She taught at the Zhukovsky Air Force Engineering Academy and later at the Moscow State University of Railway Engineering.
So it sounds like her life was deeply rooted in academia for many years. When did she make the leap into writing fiction?
It seems the world of literature beckoned later in life almost like a second act. And she found remarkable success there, too. One of her novels, Hostess, was even adapted into a film called Bless the Woman.
That's amazing. It's like she had these two parallel passions, both flourishing in their own right. What a remarkable life.
Truly inspiring.
It is. But let's get back to the reason we wanted to deep dive into Grekova. Her textbook, Probability Theory, First Steps. Have you had a chance to take a look?
I have.
And I have to admit, for a math textbook, it's surprisingly engaging.
Yeah.
It's definitely not the dry, formula-heavy kind of book I was expecting. In fact, she starts with a humorous anecdote about a student who misunderstood a fundamental concept. Thinking a probability greater than 1 meant something was more probable.
Oh, that's a classic misconception. It highlights how our intuition about probability can sometimes lead us astray.
For sure.
Grekova uses it to emphasize the importance of understanding the basic principles, like the idea that the probability of a sure event is 1 and the probability of an impossible event is 0. Everything else falls somewhere in between.
And those in-between probabilities, that's where things start to get interesting.
Exactly. And that's what Grekova sets out to explore in her book.
So let's take a step into her world. What's the first chapter all about?
Well, in Chapter 1, Probability Theory and Its Problems, Grekova lays the groundwork. She starts by defining what we mean by a random event and introduces the concept of a sure event to establish the unit of measurement for probability.
Okay.
She uses the Soviet sport lottery as an example, bringing probability into a real-world context.
I like that.
Suddenly, it's not just theoretical numbers, it's about chances, possibilities, maybe even winning some rubles.
It's like she's saying, hey, this isn't just abstract math, this stuff matters.
Exactly, and she builds on that foundation by introducing the idea of practically sure versus practically impossible events. It gets you thinking about how we make decisions in our own lives when faced with uncertainty.
Like weighing the odds and making informed choices based on the probabilities at play. That's a valuable skill in any situation, right?
Absolutely. And that brings us to Chapter 2, where Grekova delves into the relationship between probability and frequency.
Okay, so we're moving from the foundational concepts to the nitty-gritty of how we actually measure and estimate probabilities. What's the key takeaway here?
Well, she starts by explaining that you can't always rely on that classical model of equally likely outcomes, especially when you're dealing with real-world scenarios. So she introduces the concept of frequency, essentially how often something happens in a series of repeated experiments.
So instead of just assuming equal probabilities, we look at actual data, real-world observations, to figure out how likely something is to occur.
Precisely. And that leads to a fascinating concept. The idea that as we gather more and more data, the frequency of an event tends to stabilize around a certain value.
Almost like order emerging from chaos. Is that what she means by the relationship between probability and frequency?
Exactly. It's like glimpsing a hidden pattern in the randomness. Grekova even illustrates this with Carl Pearson's famous coin-tossing experiment, where he flipped a coin thousands of times to demonstrate this principle.
It's amazing to think that even renowned scientists were captivated by this interplay between chance and predictability. It makes you want to try it yourself, right? Flip a coin 100 times and see how the frequencies play out.
It's a great way to get a feel for this fundamental principle. And from there, Grekova takes us deeper into the world of probability, with Chapter 3 focusing on the fundamental rules that govern how we calculate probabilities.
Okay, so this is where we start getting into the nuts and bolts of probability calculations. I'm ready to put on my mathematical thinking cap.
You'll need it. Chapter 3 introduces two key rules, the summation rule and the multiplication rule. These are the building blocks for understanding more complex probability scenarios.
Sounds intriguing. Let's start with the summation rule. How does that work?
Well, the summation rule comes into play when you're dealing with events that can't happen at the same time. Grekova calls these mutually exclusive events.
Okay, so like flipping a coin. You can get heads or tails, but you can't get both at the same time. Those are mutually exclusive events.
Exactly. And the summation rule tells us that the probability of either one of those events happening is simply the sum of their individual probabilities.
Okay, so if the probability of getting heads is 12, and the probability of getting tails is 12, the probability of getting either heads or our tails is 12 plus 12, which equals 1. That makes sense. It's a sure event.
You got it. It's a straightforward rule, but it lays the foundation for understanding more complex scenarios.
Okay, so what about the multiplication rule? When does that come into play?
The multiplication rule is all about combined events, where you're looking at the probability of two or more things happening together, and this is where the concept of dependent versus independent events becomes crucial.
Ah, so that's where those coin flips come back into the picture. Just because I get heads 5 times in a row doesn't mean I'm any more likely to get tails on the 6th flip. Each flip is independent of the others.
Exactly. And for independent events, the multiplication rule is simple. You just multiply the probabilities of each individual event to get the probability of them all happening.
So if I flip a coin 4 times, the probability of getting heads all 4 times is 12 times 12 times 12 times 12, which is 116. It's like the probability shrinks with each additional event.
You're getting it.
Yeah.
But things get a bit trickier when we're dealing with dependent events, where the outcome of one event influences the probability of the next. Grekova uses the example of drawing marbles from a bag without putting them back in to illustrate this concept.
Right, because if you take out a red marble, it changes the probabilities for the next marble you draw. The events are linked.
Precisely. And in those cases, we need to consider conditional probability, the probability of an event happening, given that another event has already occurred. It adds another layer of complexity to the calculations.
I'm starting to see how mastering these rules can be so powerful. It's like unlocking a secret code to understanding how chance and probability work in the real world.
It is, and Grekova doesn't shy away from challenging her readers with increasingly complex scenarios, like calculating the probabilities involved in target shooting with multiple riflemen. It's a great way to stretch those probability muscles.
I can imagine. But
Yeah.
she always breaks it down step by step, right? So even if a problem seems daunting at first, you can follow her logic and arrive at the solution.
Exactly. And she also emphasizes the importance of considering the opposite event, especially when you're dealing with problems that involve the phrase "at least." Sometimes it's easier to calculate the probability of something not happening and then subtract that from 1 to find the probability of it happening.
It's like a clever shortcut to simplify the calculation. I'm starting to see why this book is considered a classic. It's not just about memorizing formulas, it's about developing a deeper understanding of how probability works.
And she uses such engaging examples, like the birthday problem, where she demonstrates that in a group of just 23 people, there's a greater than 50% chance that at least 2 people will share the same birthday. It's a classic example of how probability can lead to counterintuitive results.
It's mind-boggling when you first hear it, right?
Yeah.
You wouldn't expect those odds with such a relatively small group of people.
It really highlights the power of probability theory to reveal hidden patterns and surprising insights. And that brings us to chapter 4, where Grekova introduces the concept of random variables.
Okay, so we're moving into new territory now. What are random variables and why are they important in probability theory?
A random variable is essentially a quantity whose value is determined by chance. It could be something like the number of heads you get when flipping a coin, or the height of a randomly selected person, or the temperature in a city on a given day.
So it's a way of representing those elements of randomness that we encounter in so many situations.
Exactly. And Grekova distinguishes between two types of random variables: discrete and continued. Discrete variables take on distinct, separate values, like the number of students in a class. Continuous variables, on the other hand, can theoretically take on any value within a certain range, like a person's height or weight.
So the type of random variable dictates how we approach probability calculations.
Precisely. And with continuous variables, Grekova introduces a fascinating concept: the idea that the probability of a continuous variable taking on any specific value is actually zero.
Wait, what? How can that be? It seems counterintuitive.
It does, doesn't it? But think about it this way. A point on a line has zero length, yet a line is made up of an infinite number of points. It's a paradox. And it's similar with continuous random variables.
So instead of focusing on the probability of a single value, we look at the probability of the variable falling within a certain range.
Exactly, and that's where the concept of probability density comes in. Grekova uses the analogy of a histogram to help visualize this. Imagine you're measuring the heights of a large group of people and plotting those heights on a histogram.
Right, so the bars on the histogram represent the number of people falling within each height range.
Exactly. And with a continuous variable, as we gather more and more data, that histogram starts to smooth out and approach what we call a distribution curve. This curve represents the probability density of the variable.
So the higher the curve, the more likely the variable is to fall within that range.
You got it. And Grekova then introduces two key numerical characteristics that help us understand and summarize the behavior of random variables: expectation and variance.
Okay, so expectation and variance, these are like statistical tools to make sense of randomness.
Exactly. Expectation is like the average value we would expect for the random variable if we repeated the experiment many, many times. Variance, on the other hand, measures how spread out the values are around that expectation.
So a low variance means the values are clustered tightly around the expectation, and a high variance means they're more spread out.
You've got it. And what's fascinating is that you can calculate these characteristics directly from experimental data, even if you don't know the exact distribution of the random variable. Grekova provides some handy formulas for doing just that.
It's like having a powerful toolkit for analyzing and making sense of data, even when there's an element of randomness involved.
It is. And it lays the groundwork for what Grekova calls indirect methods for calculating probabilities, which she introduces later in the chapter.
Okay, so indirect methods, that sounds intriguing. It's like we've mastered the basic rules and now we're moving into advanced probability techniques.
You could say that indirect methods are all about using the probabilities of related events to figure out the probability of something else. It's like being a probability detective, piecing together clues to solve a mystery.
I'm ready to put on my detective hat. How do these indirect methods work in practice?
Well, imagine you want to find the probability of a complex event, like let's say a machine breaking down.
Okay, a machine breaking down.
Instead of trying to calculate that directly, you might look at the probabilities of individual components failing.
So like the probability of a motor failing or a belt snapping or a circuit shorting out.
Exactly. And by understanding the relationships between those simpler events and the overall breakdown, you can use those probabilities to work your way back to the probability of the whole machine failing. It's a pretty brilliant approach.
Yeah, it's like breaking down a complex problem into smaller, more manageable pieces. Than using those pieces to solve the bigger puzzle.
Exactly. And those numerical characteristics we talked about, expectation and variance, those play a crucial role in these indirect calculations.
Right. Okay. Remind me how those fit into this detective work.
Well, remember the additivity of expectation? The expectation of a sum of random variables is just the sum of their individual expectations.
Okay. Yeah.
So if we know the expected number of times each component is likely to fail in a year, we can add those up to get the expected number of times the whole machine might break down. And the same principle applies to variance. As long as those component failures are independent events, we can add up their variances to get the overall variance for the machine breaking down.
So with just these simple rules, we can start to make predictions about complex events. based on our understanding of simpler ones. It's like having a secret decoder ring for the world of probability.
It is powerful stuff. And Grekova illustrates this beautifully in Chapter 4 with a problem about calculating the number of times an event occurs in a series of independent trials.
Right, I remember that one. It really brings those additivity rules for expectation and variance to life.
It does. It shows how those seemingly abstract concepts can be applied to solve real-world problems.
Yeah.
And it really underscores Grekova's talent for making complex ideas accessible.
Well, I think we've covered a lot of ground today, from Irina Grekova's fascinating life story to the foundational concepts of probability and even those mind-bending indirect methods. It's been quite a journey.
Yeah, it has. It really highlights the beauty and power of probability theory. It's a lens through which we can understand and even predict the randomness that surrounds us.
Definitely. And I have to say, Grekova's ability to explain these concepts in such a clear and engaging way is truly remarkable. Who knows, maybe this deep dive will inspire some future mathematicians or novelists out there.
One can only hope.
So as we wrap up this deep dive, I want to leave you with a question. Where do you encounter randomness and uncertainty in your own life? How might understanding the basic principles of probability help you navigate those situations? It's something to ponder as you go about your day.
A great question to keep in mind.
And if you enjoyed this deep dive into the world of Irina Grekova and probability theory, don't forget to leave us a 5-star rating on Spotify and Apple Podcasts. Until next time, keep exploring, keep learning, and keep diving deep.